Welcome to section 7.3, the central limit theorem, or CLT, arguably the most important theorem in introductory statistics. This powerful concept explains why the sample mean behaves so predictably when we take random samples, even from a population that doesn't look normal at all. Let's say Tony Stark is monitoring arc reactor performance. Each reactor's output might be unpredictable and even skewed. But if he takes multiple samples and calculates the average output each time, those averages will start to form a bell-shaped normal distribution. That's the magic of the CLT. It tells us that no matter what the population distribution looks like, the distribution of the sample mean becomes approximately normal as the sample size increases. And that's the key to making confident predictions. Before we apply the central limit theorem, there are a few conditions that must be met. First, random sampling. Our data must come from a random process. If we only sample friends or volunteers, the results may be biased. Second, finite mean and standard deviation. The population must have a real average and a measurable spread. Third, the sample size, N. If the population is already normal, any sample size works. But if it's skewed or has outliers, we usually want N to be greater than or equal to 30. This is why survey researchers, engineers, and scientists often aim for larger samples to reduce the effect of irregularities in the population and activate the power of the CLT. Let's get nerdy for a second. Iron Man's arc reactor outputs power inconsistently due to external forces, maybe from battles or the occasional sabotage by Ultron. The individual output data is heavily skewed with a mean of 1,000 units and a standard deviation of 200. Tony takes 40 measurements of output and computes the average. According to the central limit theorem, the distribution of these sample means will be approximately normal, even though the individual readings aren't. This is a perfect example of how the CLT helps us smooth out unpredictability and make informed decisions, whether you're tuning a reactor or testing marketing campaigns. Let's break this down further. When we take samples and compute their means, the mean of all those sample means is equal to the population mean, mu. The standard deviation of the sample means, called the standard error, is sigma divided by the square root of n, our population standard deviation, divided by the square root of the sample size. So if we take larger samples, that denominator gets bigger and the standard error gets smaller, meaning our estimates get more precise. It's like zooming in with a higher resolution lens. You'll see the true average more clearly. Here's a fun way to visualize the CLT in action with dice. If you roll a single die, each number 1 through 6 is equally likely. That's a uniform distribution. Now roll 2 die, average the result, and repeat. You'll start seeing a bump in the middle, more 6s and 7s for the average, fewer extremes. Roll 10 dice, average their faces, and repeat. You'll see a nice bell curve. This shows how even from flat or weird distributions, the average becomes normal. That's the CLT. Let's revisit the formula for the standard error, which is the standard deviation of the sampling distribution of the mean. It's the standard deviation of the population divided by the square root of the number of observations. The bigger the sample, the more information we have, and the smaller our uncertainty. This matters in every context, whether you're measuring light levels in Stark Tower or polling students about their screen time. A smaller standard error means your sample mean is hugging the true mean more tightly. Let's apply everything with a real example. Suppose the average commute time to campus is 28 minutes, with a population standard deviation of 7 minutes. You take a sample of 36 students. The standard error is 7 divided by the square root of 36. You want to find the probability that this sample mean is less than 27 minutes. So, convert it to a z-score. We would go z equals 27 minus 28 over our standard error, 1.17. So if we throw this to calculator, we're going to get about 0.85. All right, so if we look at a normal distribution, right? A standard normal distribution, we know that means our mean's at 0 and standard deviation of 1. So negative 0.85, I'm missing my negative sign up here. Missing my pen. There we go, negative. Negative 0.85 means that we're looking at this probability of less on a normal table. So we can look that up on a normal table or use one of the websites I gave you before, like this one. We're going to find that that probability is about 0.1977. So there's about a 20% chance that a sample of 36 students has an average commute under 27 minutes. Let's wrap up. The central limit theorem tells us that the sample mean follows a normal distribution as sample size increases. This lets us use probability to estimate how far off a sample mean might be. The standard error quantifies how variable those sample means are. Whether you're building suits like Iron Man, managing travel budgets, or polling customers, the CLT and standard error help you trust your data.